Hello everyone and very good evening to all of you. Good evening everyone, good evening. Am I audible, visible? Okay, so once again welcome to Wallah. So I hope you are doing well. Now in this session we will solve some problems so that we will revise our concept. Okay, so let's start this session. Let's start this session. Okay, so this is the first question. This is the NAT type of question. This is the NAT type of question. Good evening, Mithun. Good evening. This is a NAT type of question. So first, please read the question carefully. First, read the question carefully. Please read the question carefully. In this question, it is given that the temperature variation across a wall, which is 0.3 meter thick at a certain instant of time, is T of x is equal to a plus bx plus cx square, where T is a temperature which is in degree Celsius and x is in meter. The value of A is given, B is given, and the value of C is also given, right? The wall has a thermal conductivity of 1 watt per meter Kelvin. If the cold surface is exposed to the fluid at 100 degrees Celsius, what is the convective heat transfer coefficient, right? In question, convective heat transfer coefficient is asked. What is the convective heat transfer coefficient? In this question, convective heat transfer coefficient is asked. Okay, now see. This question is like this. Okay, now see. The temperature variation across a wall. So there is a wall. This is the wall. And this wall is 0.3 meter thick. This wall is 0.3 meter thick. Correct. And the temperature variation is given, and that is given T of x is equal to that is 200 minus the value of B is given 200x plus the value of C is given 30 x square. So this is the variation of temperature. Wall thermal conductivity is given, which is K is equal to 1 watt per meter Kelvin. 1 watt per meter Kelvin, right? If the cold surface is exposed, right? So what is the cold surface? What is the cold surface? Now see here. Let us assume this is the x is equal to 0. If this is the x is equal to 0, so definitely this is the x is equal to 0.3 meter. 0.3 meter. Correct. Now put the value x is equal to 0. So T of 0 is equal to, this is 200. And if I ask you what is the T of 0.3, put the value of x is equal to 0.3. Now what is the T of 0.3? Right. So this is 200 minus 200 into 0.3 plus 30 into this is 0.3 square. Okay. Now see, from here you can calculate the temperature of the right face. So 200 minus 200 into 0.3, 200 into 0.3 plus 30 into that is 0.3 square. So this temperature comes 142.7 degrees Celsius. That means this is the left face and this is the right face. So what is the temperature at the left face? The temperature at the left face is 200 degrees Celsius. Here the temperature is 200 degrees Celsius. And what about the temperature here? Here the temperature is 142.7 degrees Celsius. Correct. So it is given in the problem. It is mentioned in the problem. It is mentioned in the problem, the cold surface is exposed to the fluid which is at 100 degrees Celsius. Okay, so this is the cold surface, and this cold surface is in contact, this cold surface is in contact with the fluid, or I can, fluid is in contact with the fluid which is at 100 degrees Celsius. So T infinitive is equal to 100 degrees Celsius. This is given in the problem. So convective heat transfer coefficient, what is the value of H? This is asked. What is the value of H? Fine. Now see here. See, apply the energy balance at x is equal to 0.3 meter. Apply the energy balance here. Apply the energy balance at x is equal to 0.3 meter. Apply the energy balance. Apply the energy balance here at x is equal to 0.3 meter. So if you apply the energy balance, you can say the rate of conduction heat transfer at x is equal to 0.3 meter is equal to rate of convection heat transfer. Right? This is a very simple energy balance. Whatever the conduction at x is equal to 0.3 meter, the same is equal to the rate of convection heat transfer to the fluid also. Right? So if you apply the energy balance, so you can say, if you apply the energy balance, you can say, if you apply the energy balance, you can say, right, rate of conduction heat transfer, rate of conduction heat transfer, rate of conduction heat transfer at x is equal to 0.3 meter. This is equal to rate of convection heat transfer to the fluid, rate of convection heat transfer, rate of convection heat transfer to the fluid, rate of convection heat transfer to the fluid. So what is the rate of conduction heat transfer at x is equal to 0.3 meter? So if you apply the Fourier law of heat conduction, so you can say this is minus in k into a, and this is dt by dx. This is dt by dx at x is equal to 0.3 meter, and this is equal to, this is h into a, and this is tw minus, this is t infinitive. Tw minus T infinitive. And what is a Tw? Tw is a wall temperature. Correct. Now A and A is cancel out. Right. Now calculate the dt by dx at x is equal to 0.3 meter. So temperature variation is given. So calculate the dt by dx. dt by dx. So what is the dt by dx? This is minus 200. Minus 200 plus. Minus 200 plus this is 60x. This is 60x, correct? Now this is 0 minus 200 plus 60x, and dt by dx is asked at x is equal to 0.3 meter. 0.3 meter. So put the value of x 0.3. So this is minus 200 60 into 0.3. 60 into 0.3. Correct? Na? 60 into 0.3. So it comes minus 182. It comes minus 182 degrees Celsius per meter. Right? Minus 182. Is it okay? Is it clear or not? Now see here. So this is K. Thermal conductivity is given in the problem, which is given 1 watt per meter Kelvin. So this is 1 minus 1 minus 182. This is equal to H into TW. What is the TW? The value of TW is 142.7. 142.7 minus, what is the T infinitive? The T infinitive is given 100 degrees Celsius. So this is 100 degrees Celsius. Now calculate the H from here. Calculate the H, and this comes in watt per meter square Kelvin. So calculate the H. What is the H? Tell me. What is the H? Tell me. What is the value of H? Tell me what is the value of H? So the value of H is, this is 182 This is simple calculation. Now 182 divided by 142.7 minus 100. So it is 42.7. So the value of H is 4.262. This is the value of H. This is the value of H. Please cross check the calculation now. Please cross check the calculation. It comes 4.262 watt per meter square Kelvin. This is the value of H. So please check the calculation. Please check the calculation once. Okay. Now come to the next problem. Okay. So next question is also NAT type of question. Next question is a NAT type of question. Next question is a NAT type of question. Okay, now see the next question. In the next question, it is given that steam is condensed at a temperature of 50 degrees Celsius, and HFG, the latent heat of condensation, is also given. That is, the HFG is the latent heat of condensation. So latent heat of condensation is 2383 kilojoule per kg. With cooling water, specific heat is given 480 joule per kg degree Celsius, as shown in the figure. The water enters the tube of the condenser at 18 degrees Celsius and leaves at 27 degrees Celsius. The surface area of the tube is 42 meter square and the overall heat transfer coefficient is 2400 watt per meter square degree Celsius. So in the question it is asked, what is the rate of condensation of the steam in the condenser is? What is the rate of, in the question it is asked, what is the rate of condensation of the steam in the condenser is? So basically, this is the problem of the condenser type of heat exchanger, right? This is the problem of the heat exchanger, and steam is condensed here. So basically, this is a condenser type of heat exchanger. Okay, now see here. If you draw the temperature profile, and see, we know that in case of the condenser type of heat exchanger or evaporator type of heat exchanger, right? Either your flow is parallel or counter flow, it is doesn't matter, right? Because see, if I'm talking about the condenser type of heat exchanger or evaporator type of heat exchanger, so in such type of heat exchanger, right, that effectiveness or LMTD, right, it is independent of the direction of motion of the fluid, right? That means you have, either you consider as a parallel flow or you can consider as a counter flow, your end result will be same. Getting my point? Right. Now see here. Now see. So your steam is condensed, correct? Steam is condensed. So see here. Okay, so this is the THI. This is the hot fluid inlet temperature. This is the hot fluid exit temperature, right? Hot fluid inlet temperature and the hot fluid exit temperature. So since steam is condensate, hot fluid inlet temperature and hot fluid exit temperature will be same, and that is given 50 degrees Celsius. The saturation temperature is given 50 degrees Celsius. So this temperature is 50 degrees Celsius. Cooling water, water enters the tube of the condenser at 18 degrees Celsius and leaves. That means cold fluid is water. Cold fluid is water. See, the cold fluid is water. So the temperature of the water increases. So inlet temperature of the cold fluid, this is given in the problem, 18 degrees Celsius. 18 degrees Celsius. And the exit temperature of the cold fluid, this is equal to 27 degrees Celsius. This is given 27 degrees Celsius. Correct. Now, In this question, it is asked what is the rate of condensation of steam in the condenser is. Correct. So in the question, it is asked what is the mass of the steam or what is the rate of mass of the steam condensate. It is asked in the question. Fine. Now see here. Now see. So what is the first? First tell me what is the latent heat of condensation. What is the latent heat of condensation release? Because steam is condensate. So if steam is condensate, so definitely the latent heat of condensation is released. Now what is the latent heat of condensation released here? So simply we can say this is equal to m dot s, right? The mass of the steam which is condensate into this is the latent heat of condensation. This is the latent heat of condensation. Correct, na? So from the energy balance we can write, right? From the energy balance we can write that Q dot is equal to, right? This is the m dot s multiplied by HFG. This is the latent heat of condensation released, right? This is the latent heat of condensation released, and this is equal to, we can say this is equal to U into A into LMTD. We can say the U into A into LMTD. Is it fine? Now see here. Can we calculate the LMTD here? Can we calculate the LMTD here? Yes, we can calculate. So at x is equal to 0, this is the x is equal to 0, and this is the x is equal to L, right? So what is the theta here? What is the theta 1? Sorry, temperature difference. So 50 minus 18, right? 50 minus 18. So 50 minus 18, 50 minus 18, this is 32. This is 32. And what is the theta 2? The theta 2 is equal to 50 minus 27. 50 minus 27, that is equal to 23. That is equal to 23. So what is the LMTD? What is the LMTD? So LMTD is equal to theta 1 minus theta 2. Theta 1 minus theta 2 divided by natural log theta 1 by theta 2. Now calculate the LMTD. Calculate the LMTD. So theta 1 is 32 minus theta 2 is 23. Natural log 32 divided by 23. So it comes 27.252. 27.252. Right? This is the LMTD. Right? This is the temperature difference. Now, this is the temperature difference. Again, I am repeating, this is the temperature difference. This is a logarithmic mean temperature difference. Right? This is the logarithmic mean temperature difference. So either you use the degree Celsius or Kelvin. Right? In degree Celsius, in Kelvin, result will be same. See, again I am repeating the LMTD. LMTD is 27.252. Right? So you can say 27.252 degrees Celsius or you can say 27.252 Kelvin. Right? Ultimately, this is the temperature difference. Okay. Now see, if you calculate the LMTD in degrees Celsius, you are getting the same value. If you calculate the LMTD in Kelvin, you are getting the same value. 27.252 only. Now see here. So m dot s, it is asked what is the mass flow rate, or sorry, what is the rate of condensation of steam. In question it is asked, right? So your LMTD is 27.252. U is given in the problem that overall heat transfer coefficient is 2400. It is 2400 multiplied by area is also given in the problem, that is 42 meter square. 42 meter square into LMTD, that is 27.252. 27.252 divided by the HFG. And what is the HFG? That is 2383. That is a 2383. 2383. Right. So calculate the m dot s from here. 2383. So calculate the m dot s. Tell me what is the m dot s. Tell me what is the m dot s. So this is 2400 into 42 into 27.252 2383. Right. Please shake. 2400, the overall heat transfer coefficient is in watt, na? Okay, this is in kilojoule per kg, correct. So this is 1000. This comes 1.152. This comes 1.152 kg per second. 1.152 kg per second. So this is the steam rate which is condensate. This is the m dot s. Please cross check the calculation. Please cross check the calculation. So in question it is asked what is the rate of condensation of steam. So this is the rate of condensation of steam. 1.152 kg per second. 1.152 kg per second. Is it clear? Okay, now come to the next question. Come to the next question. Okay, come to the next question. This is the NAT question. This is the NAT question. Okay, now see this is a NAT question. So please read the question carefully. Okay, and in this question it is given that a conical section fabricated from pure aluminium. It is of circular cross section having diameter d is equal to ax to the power 1 by 2, where x is in meter and a is 0.5 meter to the power 1 by 2. And the small end is located at x1 is equal to 25 mm and the large end is located at x2 is equal to 125 mm. The end temperature are T1 is equal to 600 Kelvin and T2 is equal to 400 Kelvin. While the lateral surface is insulated, the rate of heat flow in kilowatt is, right? And thermal conductivity of the aluminium, this is also given, that is 236 watt per meter Kelvin. 236 watt per meter Kelvin. Okay, now see here. This is the conical section. 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 And the lateral surface is insulated. It is given in the problem. Lateral surface is insulated. Lateral surface is insulated. This is the center line. Okay. Now see here the diameter changes with respect to x, and the variation of or dependency of diameter with x is d is equal to a x to the power 1 by 2, ax to the power 1 by 2, where x is in meter and the value of a is also given. So you can say this is 0.5 x to the power 1 by 2, correct. The small end is located, x1 is equal to 25 mm, x is equal to 25 mm, and the bigger end or large end is located, x2 is equal to 125 mm, 125 mm, and the temperature is given T1. So at this location, at this section, temperature is 600 Kelvin and at this section the temperature is 400 Kelvin, right? So temperature difference exists, and because of the temperature difference, right, conduction heat transfer occurs through this, conical section. So let us assume the rate of conduction heat transfer through this conical section is Q dot. Correct. Now in the question, this, what is this Q dot? This Q dot is asked. What is the rate of heat flow? Okay. Now see here. For the calculation of Q dot, what I am doing here, I am considering a very small element. At a distance x from the small end. I am considering a small element at a distance x. So this distance is x, and this dimension is, you can say, this is the dx. The thickness is dx. And what is the area? Of this small element? So I can say the area of this small element is ax. And what is the diameter of this small element? That is a dx. And what is the temperature difference across this small element? So temperature difference across this small element, that is dt. And what is the rate of conduction heat transfer through this small element? The rate of conduction heat transfer through this small element is, that is dq dot. So can we apply the Fourier law of heat conduction here for this small element? Can we apply the Fourier law of heat conduction? Can we apply the Fourier law of heat conduction for this small element? Yes, we can apply the Fourier law of heat conduction. So from the Fourier law of heat conduction, from Fourier law of heat conduction, from Fourier law of heat conduction, we can say the dq dot is equal to this is minus k a, and this is the dt by dx or ax. Correct. Now see here, if I ask you what is the relation between the dq dot and the q dot, because this q dot is not a function of x. The q dot is not a function of x. It is not a function of x. If you ask me what is the rate of conduction heat transfer at this section, I am saying this is q dot. If you ask me what is the rate of conduction heat transfer here, that is a q dot. So your q dot is not a function of x. If your q dot is not a function of x, that means in the x direction, the q dot is a constant, and we can say the dq dot is equal to q dot only. Right? That dq dot is equal to q dot only. Correct? Now see here, dq dot. So dq dot is equal to, this is q dot into dx is equal to, this is minus into, what is ax? So this is pi by 4 dx square, and this is dt. Now tell me what is dx? The dx is equal to 0.5 x to the power 1 by 2. So you can say this is minus k into pi by 4 into, right, dx. This is 0.5 x to the power 1 by 2. 0.5 x to the power 1 by 2 square dt. Right? And this is q dot into dx. Now q dot into dx. Now see here, this is x is equal to minus, the value of k is given 236. The value of k is given, this is 236 into pi by 4 into, this is 0.5 square, and this is dt. Now integrate this equation. Right? So 236 is constant, pi by 4 0.5 square constant. Integrate from where to where? From x1 to x2. And what is the x1? 25 mm. So 0.025. because x is in meter na, so 0.025 to 0.0 sorry 125, so 0.125 0.125, and corresponding to this, what is the temperature? The temperature is 600 Kelvin. This temperature is 600 Kelvin and this temperature is 400 Kelvin. Correct na? Okay. Now solve this. So Q dot into ln natural log, this is 0.125, right? ln 0.125, 0.025 is equal to, this is minus 236 into pi by 4 into 0.5 square into, this is 400 minus 600. 400 minus 600. So tell me what is the Q dot? Now tell me what is the Q dot? What is the Q dot? So this is 236 into 236 into 0.785 into 0.5 square. 0.5 square into 200, and this is ln 0.125 divided by 0.025. So this value comes 57, the Q dot. Please check the calculation. Now the Q dot is equal to, this is 5755.425 watt. So in kilowatt it is 5.755 kilowatt. This is the Q dot, right? This is the Q dot, 5.755 kilowatt. Please check the calculation. 5.755 kilowatt. Please check the calculation. 5.755, and it is asked in the kilowatt, so it is 5.755 kilowatt, right? 5.755 kilowatt. So this is the correct answer. This is the correct answer. Okay, now come to the next question. Come to the next question. Okay, so this is a MSQ question. This is the MSQ question. Please see the next question. This is a MSQ question. So tell me what would be the answer. Tell me what is the answer. Tell me what is the answer. This is a MSQ question. Which one or more of the following statement are correct? The statement A says, wavelength at which monochromatic emissive power of a black body is maximum is shifted towards the right side with increasing temperature in EB lambda versus lambda graph. This statement is correct. This statement is correct or wrong? This statement is true or false? This statement is true or false? Okay, so if you are observing the EB lambda versus lambda graph, if you are observing EB lambda means monochromatic emissive power of a black body. So if you are observing EB lambda versus lambda graph, so this is the graph. See here. Right, this is the graph. Right, now see here. This graph is corresponding to, let us assume this is corresponding to 600 Kelvin. This graph is corresponding to, let us assume this graph is corresponding to 800 Kelvin. And this graph is corresponding to, let us assume, corresponding to 1000 Kelvin. Okay, now focus on the peak of the graph. Peak. See here. See here. So the peak of the graph is shifted. Peak. Okay, now see here. See here. So this is the peak of the graph. No? This is the peak of the graph. Corresponding to this temperature, the monochromatic emissive power is maximum here. Corresponding to this temperature, monochromatic emissive power is maximum. This is the maximum monochromatic emissive power. And corresponding to this temperature, this is the maximum monochromatic emissive power. Is it okay now? See here. Now, in the question, in the statement A says wavelength at which monochromatic emissive power of the black body is maximum is shifted towards the right side. Now see here. The wavelength at which, so here it is lambda max 1, it is lambda max 2, it is lambda max 3, right? And the lambda max is not a maximum wavelength. It is a wavelength at which monochromatic emissive power of a black body is maximum, right? Lambda max is not a maximum wavelength. It is not a maximum wavelength. It is a wavelength at which the monochromatic emissive power of a black body is maximum. Getting my point? So this lambda max is shifted towards the left hand side. It's shifted towards the shorter wavelength side as you increase the temperature, right? As you increase the temperature, the wavelength at which monochromatic emissive power is maximum shifted towards the shorter wavelength side, right? That means it is shifted towards the left hand side, not the right hand side. So this statement is wrong. Statement A is absolutely wrong. Statement A is wrong. Now come to the statement number B. The statement B says the maximum monochromatic emissive power of a black body is directly proportional to the fourth power of the absolute temperature. No. See here. EB lambda, which is a EB lambda max. This is the maximum monochromatic emissive power. Right? This is the maximum monochromatic emissive power. The maximum monochromatic emissive power is directly proportional to T to the power 5. It is directly proportional to T to the power 5. Not T to the power 4. It is directly proportional to T to the power 5. So statement B says, see, the total emissive power of a black body, that is directly proportional to T to the power 4. The total emissive power of a black body. But if I'm talking about the maximum monochromatic emissive power of a black body, so the maximum monochromatic emissive power of a black body is directly proportional to the fifth power of the absolute temperature. Fifth power of the absolute temperature. So that's why this statement is wrong. The statement B is wrong. The statement B is wrong. Okay, now come to the statement number C. A black body is a perfect emitter. Yes, this is absolutely correct. A black body is a perfect absorber as well as the perfect emitter, right? And also it is a diffuse emitter also. You can say diffuse emitter, right? So a black body is a perfect emitter. This statement is absolutely correct. This statement is correct. Now come to the statement number D. As per the Planck's law, when body is in thermal equilibrium with its surrounding, then emissivity of the surface is equal to the absorptivity. See here. If I'm talking about the Planck's law, so this is not a Planck's law, right? This law is correct. When the body is in thermal equilibrium with the surrounding, the emissivity of the surface is equal to absorptivity. That is correct. But this is not a Planck's law. This is the Kirchhoff's law, right? This is the Kirchhoff's law, right? So that's why statement D is also wrong. Statement D is also wrong. So, okay, just 1 minute. Which one or more of the following statement are incorrect? Sorry, I'm sorry. In this question, it is asked incorrect, na? Incorrect. So A is incorrect. A is incorrect. Statement A is incorrect. Statement B is incorrect. Statement D is incorrect. Statement C is correct. Statement C is correct. Please focus here. In question, it is asked which one or more of the following statement are incorrect. So incorrect statement we have to choose. Incorrect statement we have to choose. Right, so statement A is wrong, statement B is wrong, statement D is wrong. The statement C is correct. Okay, so what is the answer of this question? What is the answer? Answer is ABD. Answer is ABD. Is it fine? Is it clear? Okay, now come to the next problem. Come to the next problem. Come to the next question. So this is a question for 2 marks. NAT question. Please read the question carefully. Okay, so it is given that 3 infinitely long parallel plates are arranged as shown in the figure. The plate 1 and 3 are maintained at 1200 Kelvin and 300 Kelvins. So this is the plate number 1. This is the plate number 1. This is the plate number 1. And this is the plate number, right? This is the plate number 3. This is the plate number 3. So plate 1 and plate 3 are maintained at 1200 Kelvin and 300 Kelvin respectively. So T1 is 1200 Kelvin and T3 is equal to that is 300 Kelvin. The emissivity of the 3 plates are, so emissivity epsilon 1 is 0.2, epsilon 2 is 0.5 and the epsilon 3 is equal to 0.8. 0.8. If the plate number 2 received no heat from, if the plate number 2 receives no heat from the external source, the temperature of the plate 2 will be, what is the temperature of the plate 2? What is the temperature of the plate 2, right? Now see here, can we say, if you apply the energy balance, can we say the rate of radiation heat exchange between the plate 1 and 2 is equal to rate of radiation heat exchange between plate 2 and 3, right? The Q dot between 1 and 2 is equal to, this is the Q dot 2 and 3. Because if you write the thermal resistances here, right, then it is very much clear this connection is a series connection. This is, the plates are connected in series, right? Plates are connected in series. So in the series connection, we can say the rate of radiation heat exchange between these two plates, that is equal to rate of radiation heat exchange between this plate and this plate. Okay, now if you write this energy balance, if you write the energy balance, energy balance, if you write the energy balance, we can say the rate of radiation heat exchange, rate of radiation heat exchange, rate of radiation heat exchange between plate 1 and between plate 1 and 2 is equal to rate of radiation heat exchange is equal to rate of radiation heat exchange, rate of radiation heat exchange between rate of radiation heat exchange between plate 2 and 3, between plate 2 and 3. Correct. Now see here. Now see. So what is the rate of radiation heat exchange between plate 1 and 2? So Q dot net 1 2 is equal to, this is Q dot net 2 3. Correct. Now see here. Radiation heat exchange between plate 1 and 2. So we can say this is A1 sigma B T1 to the power 4 minus T2 to the power 4 divided by this is 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1, and here it is A this is A3, right, or you can say A2 sigma B and T2 to the power 4 minus T3 to the power 4 divided by, this is 1 upon epsilon 2 plus 1 upon epsilon 3 minus 1, right, 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1. Okay, now see here, what is A1 by A2? See here, what is A1 by A2? The A1 by A2, that is equal to 1 na? Two plates are infinitely long parallel plates. It is given in the problem. So A1, A2 cancel out, sigma B cancel out. Now T1 to the power 4 minus T to the power 4, T1 to the power 4 minus T to the power 4 divided by T1 to the power 4 minus T to the power 4, 1 by epsilon 1. So epsilon 1, that is 0.2, 1 by 0.2, 1 by 0.2 plus 1 by 0.5, 1 by 0.5 minus 1 by 0.2 plus 1 by 0.5 minus 1 is equal to, this is 2 T2 to the power 4 minus T3 to the power 4 divided by epsilon 2. So epsilon 2, 1 upon 0.5, 1 upon 0.5 plus 1 upon epsilon 3 is 0.8. 0.8 minus 1. Okay. Now solve this mathematical expression, because T1 is known, T3 is known. There is only one unknown, and that unknown is T2. So 1 by 0.2 plus 1 by 0.5, 1 by 0.2 plus 1 by 0.5 minus 1. So this is 6. So T1 to the power 4 minus T to the power 4 by 6. This is equal to T to the power 4 minus T3 to the power 4 divided by, this is 1 by 0.8, 1 by 0.5 minus 1. So it comes 9 by 4. It is 2.25. Okay, so this is 2.25 T1 to the power 4 minus T2 to the power 4 is equal to, this is 6 T2 to the power 4 minus 6 T3 to the power 4. Okay, so you can say this is 6 T to the power 4 plus, right, this is 2.25 T to the power 4. 6 T to the power 4 plus 2.25 T to the power 4 is equal to 2.25 T1 to the power 4 plus 6 T3 to the power 4. Okay, so this is 8.25. T2 to the power 4 is equal to 2.25 into T1 is given 1200, 1200, 300. This is 1200 plus 6 into 300 to the power 4. So 2.25 into 1200 to the power 4. 2.25 into 1200 to the power 4 plus 6 into 300 to the power 4. 8.25 1 by 4. It comes 869. What is the T2? The T2 is 869.437 Kelvin. Kelvin. This is the T2. This is the T2. Right? This is the T2. Please check the answer. Is it correct? Please check the answer. Is it correct? Okay, so this is the final answer, 869.437. 869.437. 869.437 Kelvin. 869.437 Kelvin. This is the temperature of the plate 2. This is the temperature of the plate 2. Okay, now come to the next question. Come to the next question. This is a MCQ question. 2 marks question. MCQ question, 2 marks question. Okay, now see here, a very long rectangular fin of 5 centimeter width, 1 mm thickness, 200 meter Kelvin thermal conductivity, and 40 degrees Celsius base temperature is attached to the flat plate such that the temperature at the end of the fin is same as that of the surrounding air, that is 20 degrees Celsius. Heat transfer coefficient is 20 watt per meter square Kelvin. Fin temperature at a distance of 5 centimeter from the base, and the rate of heat transfer or heat loss from the entire fin is. Now see here. So very long rectangular fin. So this is a rectangular fin. Right, this is a rectangular fin. Okay, so this is the rectangular fin and 5 centimeter width, 1 mm thickness. So this is 5 centimeter. This is 5 centimeter. And this is 1 mm thick. 5 centimeter, 1 mm thick. Thermal conductivity is given 200 watt per meter Kelvin. Thermal conductivity is given 200 watt per meter Kelvin. Right, it is given in the problem. And 40 degrees Celsius is the base temperature. So base temperature is 40 degrees Celsius. 40 degrees Celsius is the base temperature. Is attached to the flat surface such that temperature at the end of the fin is same as that of the surrounding air. See here. Please try to understand this point. Base temperature is thermal conductivity and 40 degrees Celsius base temperature is attached to the flat surface such that the temperature at the end of the fin is same as that of the surrounding air. That is 20 degrees Celsius. That means, right, that fin is so long, the temperature at the tip reaches to the ambient temperature. Right, temperature at the tip reaches to the ambient temperature. So we can say this is a problem of the infinitely long fin problem. Right, infinitely long fin problem. This is the problem of the infinitely long fin problem. Right, or I can say this is the problem of infinitely long fin. So temperature T infinitive, that is 20 degrees Celsius. Right, so this fin is so long, temperature at the tip reaches to the ambient temperature or surrounding air temperature. Now heat transfer coefficient is given 20 watt per meter square Kelvin. H is 20 watt per meter square Kelvin. 20 watt per meter square Kelvin. So what is the fin temperature at a distance of 5 centimeter from the base? Correct. So at x is equal to, in question it is asked, at x is equal to 5 centimeter, 5 centimeter or 5 centimeter from the base, what is the temperature? What is the temperature? What is the temperature? That is the first thing. And second, it is asked what is the rate of heat loss from the fin? What is the rate of heat loss from the fin? Rate of heat transfer through the fin. What is the rate of heat transfer through the fin? This is the second part. Okay, now see here. Now, this is the infinitely long fin problem. So for infinitely long fin problem, or for infinitely long fin, what is the temperature distribution? So we can say T minus T infinitive upon TB minus T infinitive is equal to e to the power minus mx. E to the power minus mx. And what is the m? The m is, this is root over HP KAC. Right, this is the m. The m is root over HP KAC. Now tell me, what is the P by AC? What is the peri? Because see, H is given, K is given. What is perimeter by cross section area? What is the perimeter by cross section area? What is the perimeter by cross section area? So perimeter is, this is a rectangular fin. So what is the perimeter? This is 2 into A plus B. Right, so A is 50 mm. This is 50 plus, that is 1 mm divided by. Now what is the cross sectional area? The cross sectional area is 50 multiplied by 50 mm. Na? I convert the centimeter into mm, so 50 mm into 1. So your P by AC, this P by AC, this P by AC is 2 into, and this is 51 divided by 50. So it comes 2.04 per mm. Okay, now see, the m is equal to this is, so what is the value of h? The value of h is 20. And the P by AC is, this is 2.04 into 10 to the power minus 3 meter. 10 to the power minus 3, right? So 20, and what is a k? K is given 200. K is given 200. So calculate m. Calculate m. So that is root over 20 upon 2.04. 20 into 2.04, and this is 10 to the power minus 3 into 200. So it comes 14.28. 14.28. Now see, so t minus T infinitive, that is 20. T infinitive is 20. Base temperature is 40 minus 20 e to the power minus, the value of m is 14.28 into value of x 0.05. 0.05. So this is e to the power minus 14.28 into 0.05 into 20 plus 20. So this comes, the temperature, this is 29.79 degrees Celsius. This is the temperature. This is the temperature. 29.79 degrees Celsius. This is the temperature. Right, 29.79 degrees Celsius. This is the temperature. 29.79. So 29.79, that means 29.8. So C is eliminated, D is also eliminated. So that answer is either A or D. Temperature is 29.8. Now calculate the rate of heat loss. So what is the rate of heat loss from the fin, or rate of heat transfer through the fin? So this is root over HPK AC, and this is TB minus T infinitive. This is TB minus T infinitive. So this is equal to, what is the value of H? That is 20. What is the value of K? That is 200. What is the value of P? So this is 2 into A plus B. So this is 50 plus 1 into 10 to the power minus 3 into, what is AC? So this is 0.05. I say 0.05 into 0.05 into 0.001 into TB minus T infinitive. So 40 minus 20. So it is 20. Okay, so calculate the rate of heat loss through the fin. Calculate the rate of heat loss through the fin. So that is root over 20 into 200 into 2 into 51 into 10 to the power minus 3 into 0.05 into 0.001 into 20. 2.856. This is 2.856 kilowatt. No, I'm sorry, this is watt, not sorry. 2.856 watt. This is the rate of heat transfer through the fin. right? This is the rate of heat transfer through the fin, 2.856. 2.856, that means 2.9. So what is the correct answer? The correct answer is A, right? A is the correct answer. A is the correct answer. Okay, now come to the next problem. Okay, now see the next question. 2 marks question. This is the NAT problem. This is the NAT problem. Okay, now see, in question it is given that long aluminium wires of diameter 3 mm are extruded at temperature of 350 degrees Celsius and exposed to the atmosphere air 30 degrees Celsius with a heat transfer coefficient of 35 watt per meter square degree Celsius. Properties of the aluminium are given. The wire is extruded at a velocity of 10 meter per minute. How far the wire travels after extrusion by the time its temperature drops to 50 degrees Celsius. So there is a long aluminium wire having the diameter 3 mm and that is extruded, right? Extrusion process is going on at a temperature of 350 degrees Celsius. So what is the initial temperature of the wire? The initial temperature of the wire is 350 degrees Celsius. Now it is exposed to the atmospheric air which is at 30 degrees Celsius. So definitely the temperature of the wire decreases with the time, or temperature of the wire changes with time, because this wire is exposed to the atmospheric air which is at 30 degrees Celsius. So see, it is very much clear this problem is based on the unsteady state, right? This problem is based on the unsteady state, right? So properties of the aluminium is given, density is given, Cp is given, thermal conductivity is given, alpha is also given, alpha, thermal diffusivity. The wire is extruded at a velocity of 10 meter per minute. So that extrusion velocity is 10 meter per minute. And in question it is asked how far the wire travels. How far the wire travels after extrusion by the time its temperature drops to 50 degrees Celsius. Right. So in this question it is asked what is the distance, what is the distance which is traveled by the wire, right, when the temperature reaches to 50 degrees Celsius. Sorry, when the temperature drops to 50 degrees Celsius. I'm sorry. When the temperature drops to 50 degrees Celsius. Yes, temperature drops to 50 degrees Celsius, or we can say temperature reaches to 50 degrees Celsius. So that initial temperature of the wire is 350 degrees Celsius. This is 350 degrees Celsius. And ambient temperature is 30 degrees Celsius. Ambient temperature is 30 degrees Celsius. Heat transfer coefficient is 35 watt per meter degree Celsius. Value of H is given 35 watt per meter square degree Celsius. Correct. And the temperature. So first calculate the at what time temperature reaches to 50 degrees Celsius. At what time the temperature reaches to 50 degrees Celsius. Right. So I first calculate the time at which temperature of the wire is 50 degrees Celsius. First calculate the First calculate the time. Okay, so see, this is the problem of the unsteady state problem, and we know that to solve the problem of unsteady state, we have the three methods. First one is the lambda parameter analysis method. Second one is a Haslett chart method, and third one is a second one is the Haslett chart method, and third one is a error function method. Right? And which method is used to solve the unsteady state problem? It is decided by the ICR and the ECR, internal conduction resistance of the solid to external convection resistance between the solid surface and the fluid, right? And see, so basically the Biot number is ratio of these two these two resistances, internal conduction resistance to external convection resistance. Okay, so first calculate the Biot number. First calculate the Biot number. What is your Biot number? What is the mathematical expression of the Biot number? Which method I used here, that is decided by ICR and the ECR. The ratio of ICR to ECR is the Biot number. So what is the mathematical expression of the Biot number? This is a HLC by KS, right? HLC by KS, correct. Now see, aluminium wire. So your aluminium wire, so that is cylindrical in shape, right? Length is not given, only the diameter is given. Okay, so you can say the characteristic length. So length is very greater as compared to diameter. Length is very greater as compared to the diameter, because it is given in the problem your aluminium wire is long. The diameter is 3 mm. So length is very greater as compared to the diameter. So L is very greater to dia. So simply we can say LC is equal to, this is V by A, and V is, this is pi by 4 D square into L divided by, what is the area? So we can say this is pi into D into L, surface area. That is the surface area. So L cancel out, pi cancel out, and sorry, D cancel out, D and D cancel out. So LC is equal to, this is D by 4. LC is equal to D by 4. So the value of H is, 35. The value of H is 35 into the value of LC, D by 4. And D is given 3 mm. D is 3 mm. So 3 into 10 to the power 3 mm. No? That means 3 into 10 to the power minus 3 divided by 4 multiplied by, what is the value of Ks? The value of Ks is, just 1 minute, 236. That is 236. So what is the Biot number? Tell me what is the Biot number. So first calculate the Biot number. Na? First calculate the Biot number. So tell me what is the value of Biot number. So this is 35 into 3 into 10 to the power minus 3. 35 into 3 into 10 to the power minus 3, and 4 into 236. So this is 1.11 into 10 to the power minus 4, which is less than 0.1. So lumped analysis is valid. Lumped analysis is valid. And if lumped analysis is valid, then temperature is only function of time, and you can write T minus T infinitive upon Ti minus T infinitive is equal to, this is e to the power minus HA rho Vc into tau. Is it fine? Now see, take the log both sides. So ln T minus T infinitive upon, this is Ti minus T infinitive, and this is equal to, this is H into tau divided by, this is rho into C into, and V by A, this is nothing but the LC. Right? This is nothing but the LC. Now solve. So ln, what is T? T is 50. This is 50 minus T infinitive. T infinitive is 30 divided by Ti. So what is the Ti? Ti is 350 minus 350 minus T infinitive is 30 is equal to minus, what is the value of H? The value of H is 35. 35 into tau divided by the value of rho. Rho is 2702. 2702 into specific heat 0.896. So 0.896 into 1000 into, convert the kilojoule into joule, na? And LC, what is the LC? LC is D by 4. So it is 3 into 10 to the power minus 3. 3 into 10 to the power minus 3. Okay. Now 4 is in numerator. Okay. Now solve. So 1010 to the power minus 3 cancel out. Okay. So first calculate the time. So this is ln 20 divided by, this is 320. 20 divided by 320. So this is minus 2.7725 is equal to minus this is 35 into 4, 2702. 2702 into 0.896 into 3. 2702.896 into 3. This is minus 0.01927 tau. Minus minus cancel out. So what is tau? This is 2.7725 0.019 2.7725.01927, and this comes tau is equal to, this is 143.876 second. This is 2.3979 minute. Okay, and the velocity is given. See, velocity is given 10 meter per minute. So velocity is equal to, this is distance per unit time. Distance per unit time. In question it is asked, what is the distance? What is the distance wire travels when the temperature reaches to 50 degrees Celsius? So distance is equal to velocity. This is 10 multiplied by 2.397. So it comes 23.97 meter. 23.97 meter. It is approximately equal to 24 meter. So correct answer is C. C is the correct answer. Okay, what is the correct answer? The correct answer is C. C for Chennai. C is the correct answer. Okay, is it clear? Okay, now come to the next problem. See the next problem. A spherical shell containing a 100-watt heat source. Inner radius and outer radius of the spherical shell are 26 centimeter and 34 centimeter respectively. Inner surface temperature and outer surface temperature are 339 Kelvin and 311 Kelvin respectively. What is the thermal conductivity of shell material? In question it is asked thermal conductivity of the shell material. Tell me what is the answer? Okay, so there is a spherical shell, correct? spherical shell like this. Spherical shell like this, and okay, this is a radius r1, this is a radius r2, right? Radius is given and 100 watt. So that 100 watt. So let us assume this is a 100 watt heat source. This is a 100 watt heat source, right? This is a 100 watt heat. So because of this 100 watt heat source, the inner temperature, so this temperature is T1, this temperature is T2. So T1 is equal to 339 Kelvin, 339 Kelvin, and T2 is equal to 311 Kelvin, 311 Kelvin, 311 Kelvin. Okay. So what is the heat energy generated by the heat source? What is the heat energy generated by the heat source? That is a 100 watt. And this 100 watt, is equal to, if you apply the energy balance, then it is very much clear, whatever the heat energy generated by this heat source in this hollow sphere, in the hollow sphere, that heat energy is propagated via conduction. Getting my point? So simply we can say, if you apply the energy balance, then we can say, if you apply the energy balance, we can say this is the heat energy generated by the heat source, and this is equal to rate of conduction heat transfer through this sphere, through this spherical shell. This is equal to the rate of heat energy generated is equal to, this is equal to rate of heat energy conducted through the spherical shell. Okay, so if you apply the energy balance, you can say rate of heat energy generated, rate of heat energy generated through the heat source, is equal to, that is equal to rate of conduction heat transfer, rate of conduction heat transfer through spherical shell, right? So rate of heat energy generated by the heat source, that is 100, and this is equal to, you can say, T1 minus T2. What is the conduction heat transfer? This is T1 minus T2 divided by R2 minus R1 divided by, this is 4 pi K R1 R2. This is a thermal resistance. Okay, so you can say this is 100 is equal to T1 minus T2. So T1, 339 minus 339 minus 311. 339 minus 311 into, this is 4 pi into K into, what is R1? 0.26.34. 0.26.34 divided by 0.34 minus 0.26. So calculate the K from this equation. Calculate the K from this equation. Tell me what is the value of K. So it is 100 multiplied by 0.34 minus 0.26. 100 into 0.34 minus 0.26. 339 minus 339 minus 311 into 4 pi into 0.26 into 0.34. Please check the calculation now. Please take the calculation. So it comes 0.257 watt per meter Kelvin. Right. This is the answer. This is the value of K. This is 0.257. 0.257 watt per meter Kelvin. This is the thermal conductivity. This is the thermal conductivity of the spherical shell. Okay, is it clear? Fine. Come to the next problem. Okay, so this is a simple problem. MSQ question, MCQ question for 1 marks. 1 marks MCQ question. So two very large parallel plates have emissivity epsilon 1 0.5 and epsilon 2 0.9. Plates are maintained at uniform temperature of T1 600 Kelvin and T2 400 Kelvin. So what is the net rate of radiation heat transfer between the two surface? So this is very simple question. So Q dot net, simply we can write, this is a A1 sigma B, T1 to the power 4 minus T to the power 4 upon, this is 1 by epsilon 1 plus 1 by epsilon 2 minus 1. And in question it is asked in the watt per meter square, correct? So area is 1 meter square. So Q dot net, right, sigma B, this is 5.67 10 to the power minus 8 into T1. T1 is given 600. 600 to the power 4 minus 400 to the power 4 divided by 1 by epsilon 1. So 1 by 0.5 plus 1 by 0.9 minus 1. Okay, so calculate the Q dot net. Calculate the Q dot net. Tell me what is the Q dot net. So this is 5.67 into 10 to the power minus 8 into 600 to the power 4 minus 400 to the power 4. And this is 1 upon 0.5 plus 1 upon 0.9 minus 1. So this comes 2793. 2793 22 watt per meter square. 2793. Right. So what is the correct answer? The correct answer is A for Agra. A is the correct answer. Okay. What is the correct answer? The correct answer is A for Agra. A is the correct answer. Okay. See this question. This is a problem based on the This is a problem based on the internal force convection. Just 1 minute. 1 minute for this. Okay, sorry. The problem. Okay, see this question. This is the problem based on the internal force convection. Okay, so it is given air at 110 kilopascal and 40 degrees Celsius enters a 6 diameter tube with a mass flow rate of 8 into 10 to the power minus 5 kg per second. The tube wall temperature is maintained constant at 140 degrees Celsius. The exit air temperature for the tube length of 14 centimeter is, right? So exit temperature, exit air temperature is asked in this question. And for the air, properties are given. Viscosity is given, thermal conductivity given, and the specific heat, the C 1.005 kilojoule per kg Kelvin. Okay, so this is a tube. Right, this is the tube. Okay, this is a tube, and tube is 14 centimeter long. Tube is 14 centimeter long, and diameter is given 6 mm. The diameter is given 6 mm, enters at 40 degrees Celsius. So bulk mean temperature TMI, this is given 40 degrees Celsius. And the mass flow rate is given, this is 8 into 10 to the power minus 5 kg per second. This is the mass flow rate. Okay, exit temperature is unknown, and the tube is maintained at constant temperature 140 degrees Celsius. So surface temperature or wall temperature is 140 degrees Celsius constant. And in question it is asked what is the exit air temperature for the tube. In question it is asked what is the TME. What is the TME? What is the exit temperature of the fluid? Now see, if you apply the energy balance here also, now first draw the temperature profile here. First draw the temperature profile. See here. Right. This is the length of the pipe L. Right. And wall temperature is constant, correct? Wall temperature is constant. Wall temperature is constant. And what is the wall temperature? Wall temperature is 140 degrees Celsius. Wall temperature is 140 degrees Celsius. This is the wall temperature. Right. And the temperature of the air increases. So this is the TMI, and this is the TME. Right. TMI is given in the problem, that is 40 degrees Celsius. This is 40 degrees Celsius. This is equal to 40 degrees Celsius. But TME, that means exit mean temperature, we don't know, and in question it is asked what is the exit, what is the mean temperature at the exit. In this question it is asked. Okay, now see, if you apply the energy balance here, if you apply the energy balance, if you apply the energy balance, you can write the rate of the rate of increase of enthalpy rate, the rate of increase of enthalpy rate of the fluid is equal to rate of convection heat transfer is equal to rate of convection heat transfer. See here, the fluid is flowing through this pipe, surface is maintained in 140 degrees Celsius. So this fluid, the temperature of the fluid is lesser than the wall temperature or surface temperature. So what is the mode of heat transfer from the surface to the fluid? That is the convection. So the rate of convection heat transfer, whatever the rate of convection heat transfer that occurs here, that is equal to the increase in enthalpy rate of the fluid. Okay, now see here, or that is equal to the increase in enthalpy rate of the air, right? Fluid is the air. So what is the increase in enthalpy rate? So you can say this is the Tm E minus Tmi, right? And this is equal to H into A. What is the temperature difference? This temperature difference is LMTD, logarithmic mean temperature difference, LMTD, right? But in this question, the value of H is unknown. In this question, the value of H is unknown. We don't know the value of H. We don't know the value of H. So first, for the calculation of the H, because see, this is the constant wall temperature, this is the constant wall temperature, but in this pipe or in this tube, the what is the condition of the flow? We don't know. The flow is laminar or flow is turbulent, we don't know. So first find out the Reynolds number. See, the mathematical expression of the Nusselt number, right? For the laminar flow, it is different. For the turbulent flow, it is different. Right. So first calculate the Reynolds number, and on the basis of Reynolds number, comment on the flow condition, type of the, what is the type of the flow inside this tube, right? And after that, we can apply the mathematical expression of the Nusselt number. So what is the Reynolds number? Can we find out the Reynolds number? So Reynolds number is equal to Reynolds number. Can we find out the Reynolds number? So this is 4 m dot divided by, this is pi into d into mu, right? Reynolds number mathematical expression 4 m dot pi d mu. So m dot is given 8 into 10 to the power minus 5, right? This is pi multiplied by d. This is 0 point, or you can say this is 6 into 10 to the power minus 3 into the value of mu 1.906. 1 minute. Na? I'm calculating here. Reynolds number is equal to, this is 4 m dot pi d mu, and this is 4 multiplied by, what is the m dot? 8 into 10 to the power minus 5 divided by, this is pi multiplied by 6 into 10 to the power minus 3 into 1.005, sorry, I'm sorry, 1.906, 1.906 into 10 to the power minus 5 kg per meter second, kg per meter second. So this 10 to the power minus 5, 10 to the power minus 5 is cancelled out. So calculate the Reynolds number. First calculate the Reynolds number. So this is 4 into 8 into 4 into 8. This is pi 6 into 10 to the power minus 3. 4 into 8. 6 pi 10 to the power minus 3 into 1.906. 906. So this value comes 890. Please check this. 890.688. This is the Reynolds number, which is less than the 2000. So flow is laminar. So flow is laminar. If flow is laminar, then Nusselt number, constant wall temperature. Constant wall temperature. So Nusselt number is equal to, this is 3.66. So constant wall temperature, correct. The Nusselt number is 3.66. Nusselt number is 3.66. Okay, and from here you can calculate the H. Okay, so what is the H? Nusselt number is 3.66. This is the flow is laminar. So please check the Reynolds number. Now please check the Reynolds number. You are getting this value or not? If you are getting this value, then flow is laminar because it is less than the critical Reynolds number. And this is a constant wall temperature case. So Nusselt number is 3.66. And Nusselt number is equal to, this is HD by KF. And this is equal to 3.66. So from here you can calculate the H. From here you can calculate the H. So tell me what is the H. So tell me what is the value of H. So this is 3.66 into 3.66 into KF. So value of K is 0.03 into diameter. This is 0.006. 0.006. Right, H, KF 3.6, 0.03 divided by D, 0.006. So it comes 18.3 watt per meter square Kelvin. 18.3. Okay, now what is the LMTD? So this is the M dot Cp. Right, this is a TME minus TMI. And this is equal to H into A. And what is the LMTD? The theta 1 minus theta 2. So what is the theta 1? 140 minus 40. This is 100. Right. And this is 140 minus 40. And this is 140 minus TME. 140 minus TME. So basically this is theta 1 minus theta 2 divided by natural log theta 1 by theta 2. 140 minus TME. Right. Now see here m dot. So mass flow rate is given, Cp is also given, TME. TME. TME is unknown. TME is unknown. What is the TMI? The TMI is 40. This is 40 is equal to the value of H, 18 point. The value of H is 18.3. This is 18.3 into, this is pi into D into L into, this is 100 minus 140. So you can say this is TME minus, this is 40 divided by natural log, and this is 100 divided by 140 minus TME. So TME minus 40, TME minus 40. This is cancel out. TME minus 40, TME minus 40. This is cancel out. Right. This is cancel out. So ultimately, there is a one equation, one unknown. One equation, one unknown. So ln 100 divided by 140 minus TME is equal to, right, 18.3 into pi into 0.006 into length is given 14 centimeter. 14 centimeter. So 0.14. 0.14 pi d into L. And mass flow rate is given 8 into 10 to the power minus 5. 8 into 10 to the power minus 5 into, what is the value of Cp? 1.005. This is 1.005 into 10 to the power 3. Okay, so calculate. So 18.3 into pi into 0.006 into 0.14. 0.14, 0.006, 18.3 into pi, and this is 8 multiplied by 1.005, 8 into 1.005 into 10 to the power minus 2. So it comes 0.6. It comes 0.6. So e to the power 0.6 and 100 divided by answer. And 140 minus answer. So this is 85. This is the answer. This TME 85.115 degrees Celsius. This is the answer. This is the TM. 85.15 degrees. 85.15 degrees Celsius. This is the correct answer. Okay, this is the correct answer. Okay, so I hope you can understand the solution of each problem. Okay, so thank you so much for this session. Thank you very much. Okay, thank you so much for this session. Thank you.